All right, this is going to be a review and solving of problem 2B.9, low density phenomena in a compressible tube flow. As the pressure decrease in system, studied in example 2.3-2, deviations from the equation, those two equations arise. Gas behaves as slips at the wall tube, so that means that the static friction, there's not going to be static friction, there's going to be kinetic friction, and the gas is going to be moving at the walls. It is conventional to replace the customary no slip boundary condition with this. And this sigma, or whatever the symbol is, I just say it's sigma because I can't really draw this, equals sigma 0 divided by pressure. And yeah, P average is just the average between the pressures at the inlet and outlet. And rho average is similarly the pressures or the densities at the inlet and outlet, the average density at the inlet and outlet. So yeah, P average is just the same as P average, but with rho. Just a little disclaimer, I won't be deriving this equation here because it doesn't explicitly ask you to derive that, so I'm not deriving that. Yeah, so we'll just get started with the momentum balance. So yeah, it's a circular tube. It's horizontal, and if you look in example 2.3, the tube is actually vertical, but if we just look at the answer that it gives us regular pressures at the inlet and outlet, so not modified pressures. So we can assume that there's no effect of pressure, or there's no effect of gravity on the pressure, because modified pressure is just the pressure. It's like it has a gravity term. So because these two pressures don't have that modified whatever, we're just going to say it's a horizontal tube. And that's why I did this. So yeah, momentum flux in the ZZ direction and ZR direction exists. I'm not actually sure. Yeah, I guess regular pressure just depends in the Z direction. I'm not sure exactly why that is. That might be because of the because usually it would be due to the gravity, but I guess it could be due to the slipping at the wall. I guess maybe that's why, as opposed to normal. If there wasn't a gravity term, the pressures would usually just not depend in the Z direction. But I guess because there's that slipping, it might depend in the Z direction. But obviously, just looking at the answer, we're going to have those terms in there. So, yeah. So with this, yeah, we eliminate this tau ZZ term, and that's because tau ZZ equals negative mu times 2 dVz dz plus some extra terms. And those extra terms we're omitting because we're saying it's a Newtonian fluid. So yeah, tau zz, negative mu 2 dVz dz, and then these terms you omit because it's your Newtonian fluid. And this term just goes to 0 because the z velocity is not dependent on the z direction, and that's because it's dependent in the r direction. It's dependent on how close the water is to the walls of the pipe. All right, so that kind of flushes that out. So yeah, momentum flux in the ZR direction. Oh yeah, and by the way, the reason this momentum flux has a pressure and this momentum flux doesn't is because, actually, let me just show you. It's because of these equations. So yeah, when the symbols are the same in the momentum flux, like XX, ZZ, YY, whatever, there's going to be a pressure. And if they're different, there's not going to be a pressure. and that's because of this sigma symbol here in this like parent equation. The sigma equals 1 if these symbols are the same, and the sigma equals 0 if the symbols are different. So the pressure term will just disappear if the symbols are different. You can see in these two equations that's what happens. And in this pi thing, the pi equals these two terms up here. So yeah, that's kind of, if you're just like getting into it, I would just recommend just looking at these second two equations here and not this first part, just for simplicity. And so yeah, back to what we were talking about before. Moment flux in the ZR direction, rho VZVR. The second term equals 0, and that's because there's no velocity in the radial direction. The liquid is only traveling through the tube, not up and down within the tube itself. And tau ZR equals negative mu dVz dr plus dVz dr, or minus mu dVz dr. Obviously, there's this mu that's distributing. And yeah, you can just see that here again from this chart here. And this term goes to 0, and that's because there's no velocity in the radial direction. Those are from table B1. So now we just write out the momentum flux equation with these terms that we got. And also, yeah, in this equation, their rho VZ VZ terms cancel out because VZ is not dependent on Z. It's not dependent in the flow direction. So at different Z values, at the same like radius, these values will be the same. So it'll just be like in the momentum flux, it'll just be like, well, actually, I haven't gotten to that part yet. I'm doing this part first, but it'll just be rho VZ VZ minus rho VZ VZ. So it'll just equal 0. All right, so now we are going to do or talk about the faces that the momentum fluxes are applied on. So the momentum flux in the ZZ direction, that's properties in the Z direction due to the Z direction. So that would be like velocity in the Z direction changing due to the Z direction. And the face that it's changing in is this face. It's the Z direction. Well, AZ is like, so like this is the Z direction. AZ is like this face. So it's the face that's perpendicular to the Z direction. It's the face that the Z direction is like looking at, the face perpendicular to Z direction. So yeah, AZ, it's a differential area. These AZ and the AR are differential areas. So imagine this is like R plus delta R, and this is R. The differential area is like the area that's between these two. So area of a circle is obviously pi r squared. So you're just going to have to take this larger circle, which includes the smaller circle, and subtract the smaller circle from it to get this area that's in between the two. So that's what I do for AZ. Equals pi times the bigger radius minus the smaller radius, and then I multiply that out. Obviously, these two terms canceling, it's pretty obvious. And then this delta r squared cancels because delta r is like an infinitely small value. It's like integration is based on like infinitely small. It's like the area under a curve. So it's like infinitely small calculations to find what is it, like slopes, or it's basically just infinitely small calculations. I don't even know how to explain it better, but so yeah, delta r is like infinitely small. So delta r squared, obviously delta r is going to be like a decimal. A decimal squared, an infinitely small decimal squared is going to be infinitely small. Obviously, if it was a big number, it would be bigger, but it's an infinitely small number, which is a decimal. So that just goes to 0 compared to 2 delta r. It's infinitely small. So yeah, just simplify. AZ simplifies into this. And this also equals 2 pi r dr instead of delta. Delta and d is like the same thing. So A in the radial direction is 2 pi r L, and that's because this radius is extending in this direction from the center line of the pipe. So it's basically just like this area. Obviously, the length of it's like the surface area of the walls of a cylinder. So this area, obviously, 2 pi or L is the length of the thing, and then times the circumference of the cylinder, which is 2 pi r, or circumference of any cylinder. I just know that. So yeah, that's where that comes from. And this area will change the momentum flux depending on the R value, because obviously there's just a regular R here. Well, it doesn't always change. Like in this, it doesn't change, but in this it does, because as R changes, for the AR direction, like this area will also expand with the little R. But as R expands for the AZ direction, AZ doesn't change. Well, the expression of AZ doesn't change, if that makes sense, which I don't know, maybe not. But it doesn't matter at all anyway, because when you divide, it just cancels out in the delta R, the R plus delta R. This delta R just it'll be like R divided by delta R plus delta R divided by delta R, and R divided by delta R will be like a really large number, and delta R divided by delta R will just be 1. So 1 compared to a really large number, you could just cancel out the 1. Or you could just say the 1 is just an inconsequential value. So you don't need to bother putting that in the momentum flux equation at all. But your teacher might want you to write it like that. So if your teacher wanted you to write it like that, you would just you would have for this equation, you would take this variable out of this parentheses here, and you would put it in here. And for this variable, it would just, you'd put parentheses and you would put R here. And for this variable, you would do parentheses and you would do R plus delta R for this one. But I didn't do that because I'm lazy, and it's not really going to affect the problem. So yeah, now we're going to substitute in the earlier defined terms and divide by 2 pi delta RL. And that's the differential volume. So it's basically just these two faces, the common terms between these two faces, or all the terms that are present in these two faces. So there's 2 pi R, delta R, and there's L. So that's how you know. Well, I mean, it's just like the differential volume. I don't even know how to explain that better, but it's just like this volume that expands out times this length. It's just, yeah. I mean, I don't know. It's differential volume. I might try to put like a picture there and post maybe a better picture of the differential volume of a cylinder. So yeah, and we're not dividing the R out, and that's because the momentum flux in the Z due to the R direction. It's due to the R direction, so it's dependent on the R direction. So you can't just divide the R out. Like all these other terms, you can divide them out because it's not dependent on that. But you can't divide the R out because like VZ is dependent on R, so you can't just divide it out. So yeah, the derivative will change the sign of the expression, and that's because a derivative is the final value minus the initial value over the final position minus the initial position, while the momentum flux is the initial value minus the final value. So yeah, just the order of the variables is changed, and the sign is, as a result, flipped. And that's why That's why this is negative. This is negative here, and this retains its sign, and that's because I moved it over to the other side of the equation. So this retains its sign because it got moved over to the other side of the equation, and this sign is flipped just because of the derivative thing, where it flips the sign compared to the momentum balance equation. So yeah. Um, Again, yeah, rho v z cancels out because they're the same at z equals 0 and z equals out. Boundary conditions. All right, so the first boundary condition is a pretty standard boundary condition that you'd see in any problem of pipe flow. At r equals 0, which is the center of the pipe, dvz dr equals 0. And that's because at the center of the pipe, the velocity is at its max, and the derivative of a max is going to be the derivative of a function at its max is 0. And that's because um, the max is like a peak of a hill. So if the slope of a peak is just a horizontal line, and the slope of a horizontal line is 0. So and the derivative of a function is the slope. So yeah, that's why it's 0. And then the second boundary condition is the boundary condition that it tells us to use, which is just this boundary condition. So yeah, those are some boundary conditions. And now we're just going to separate and integrate. Yeah, pretty simple. The integral of dx is just x, so the integral of d blop, whatever all this is just all that. And the integral of r is just r squared divided by 2 plus c1. And so yeah, that's where you get that. So yeah, now we're going to isolate this term here, and that's because that appears in one of our boundary conditions. It appears in this boundary condition, so we can isolate it, and then we can just use our first boundary condition. Yeah. So yeah, that's what we do. We isolate that term, and dvz dr equals 0 at r equals 0. So we're just plugging in all those terms. And we see in this expression, it's C1 divided by mu times 0. And so if you get an expression like this, it basically just means C1 is 0. C1 has to be 0 because if it was anything else, then the velocity would just like blow up to like infinite values, because it's just like the slope of 1 over 0 is infinity, because the y is infinitely large and the x is just infinitely small. Well, the y is infinitely large compared to the x, so it's just a vertical line, and obviously that's not the answer. So we can just say that c1 equals 0. So yeah, just put 0 in for this, and you get dvz dr equals that. Oh yeah, and by the way, for this equation up here, yeah, we're just plugging in. Oh, well, this P0 and PL are just the pressure at 0 and the pressure at L. That's kind of a... And this is just the definition of the momentum flux in the, well, plus the included R that we didn't divide out. Sorry, I didn't explain that super well earlier. Yeah. So now we're integrating a second time, and yeah, the integral of r over 2 is just r squared divided by 4 plus c2. The integral without bounds. So now we're going to have to apply the second boundary condition, and this vz value. So we already solved for dvz dr. So dvz dr is just this value here, and the c1 equals 0, so it's just this. And then it says the boundary condition is just dvz times sigma, so you just multiply the sigma. and the r is at r equals big R, because that's where the boundary condition is at r equals big R. So yeah, that's where all that came from. Yeah. So now we're just going to isolate C2 and solve for it. It's pretty simple in this case. There's just two main terms. I should have simplified at this point to or factored, but I don't know. I just didn't. That would have made the problem probably easier, but whatever. I did it at this point. That's fine. So yeah, I just plugged that C2 into this equation here, and I got this. And then I'm just factoring out this pressure conglomerate term, which is just this minus the negative sign. So yeah, r squared or just the 2. Oh yeah, r squared plus this is 2 r sigma, and that's because this 2 is here. This is 2 and not 4, so it's you can multiply that by the 2 to make it 2 in the denominator instead of 4, and then minus the r squared because there's a negative sign here. So yeah, what the problem gives the two following definitions, and I said that earlier. So, and also row average is just the same as this, but with densities. It's pretty self-explanatory. So now we're going to have to find the mass flow rate with this equation. And the mass flow rate is just the integral of the velocity over a differential area that's perpendicular to the velocity direction, which is going to be AZ, because AZ is the face that's perpendicular to the z direction, and the velocity is in the z direction. And then you're going to divide by that same area, but it's not differential, so it's just dividing by the whole area. So yeah, like we solved earlier, dA is just AZ, and AZ equals 2 pi r delta r, and then equals 2 pi r dr, because delta r is the same as dr. And A is just the total perpendicular area to the velocity direction. So that's just pi big R squared. It's pretty simple. And the radial bounds, the dA is in the R direction, so we need radial bounds. So that's why we're going from 0 to R. So yeah, now you just plug in this in here with all of these substitutions. Oh yeah, this is the average velocity, by the way. This isn't mass flow quite yet, but you can get mass flow from average velocity by multiplying by the area and rho. So yeah. So yeah, I'm just gonna remove all the unnecessary terms out of the integral, and that's by like dividing out the terms. So it would be like 2 pi and this pressure term here. And by divide out, I just basically just mean slide over to the outside of the integral. It's not like you're actually dividing really anything. I would try to not do addition or subtraction because it can mess things up. Sometimes there are situations where you might be able to do it, but it's kind of risky whether you are able to isolate things like completely incorrectly. Usually it's not. It's just usually it just won't work. So I would just not try. To be honest, it's not that much of an increased hassle. Yeah, it's not that much of an increased hassle. And if you're unsure about like this process, I would just say just don't even do it. Like you don't have to take these terms out of the integral. It just might make the integration a little more clunky. So yeah, I'm just denoting these terms as alpha in my writing just to make it so I don't have to rewrite it like a billion times. Yeah, so it's just integration. Integral of r cubed is r to the 3 divided by 4, integral of r is r squared divided by 2. And that's basically what that is there. And then inserting the bounds. It's pretty simple because it's just big R and 0. It's not that difficult. Reinserting the alpha, which is just this stuff here. And yeah, we get this equation. So yeah, mass flow rate is W, and that's the area. Again, that's the area perpendicular to the flow direction times the average velocity times rho. And that's because area is meters squared. Velocity is meters per second. So you multiply those two together, that's meters cubed per second. And these two terms together is just volumetric flow. And if you multiply volumetric flow times density, which is kilograms per meters cubed, the meters cubed and the volumetric flow cancel out with the meters cubed in the denominator of density, and the kilograms replace it, so it's kilograms per second, and kilograms per second is obviously mass flow. So yeah, that's where that kind of formula comes from. Yeah. So yeah, that's basically what I do there. It's a pretty simple thing. It just cancels out with that. And then just multiplying the rho, or density. So yeah, mass flow equals this expression. But these rho, this rho changes with r, the radius. So, and obviously you're not just going to have you're not just going to have values of rho depending on where the you're trying to find. Like, you're not just going to have values of density for different radiuses. That just doesn't make sense. So we're going to have to do some other stuff to deal with this equation. So yeah, use ideal gas law to relate density rho to pressure P. So ideal gas law, PV equals nRT, pretty standard stuff. Density can be thought of as mass per volume, kilograms per meter cubed. And the N in the ideal gas law is mass over molar mass, which equals moles. So that makes sense. So, and density is mass per meter cubed. So PV equals mass over molar mass, and obviously density equals mass over volume. So we're isolating mass over volume for density, and rho equals pressure times molar mass divided by RT. And basically what we get out of this equation is just that rho is directly proportional to pressure, or density is directly proportional to pressure. And that kind of segues into these equations here. In this example that it told us to like work off of here. Basically, it's saying the pressure divided by the density at any point along the length of the pipe is equal to the same ratio at the beginning of the pipe. So basically, this ratio should be the same at any point. So P0 divided by rho 0 equals PL divided by rho L equals PL divided by 2 divided by rho L divided by 2, and so on and so forth. So yeah, that's what this equation means, basically. So yeah, now we're going to take that equation and solve for rho. Because obviously when we looked in the answer equation, there was rho in it. So we're going to need rho somewhere, or density, rho, whatever. So yeah, rho equals P0 divided by, or rho 0 divided by rho, or divided by P0 times P. And yeah, we insert this instead of rho into the equation. So yeah, there was rho here before, and we insert this instead of rho. And now we can, since we are like, since um, pressure at different values is like a pretty normal parameter to ask for, we can expect to know those values. So um, we're basically going to separate and integrate again, and that's because we have this undefined pressure that's not defined by any specific position in the any specific position in the tube. So we're just gonna make a derivative basically. Place. Oh, well, actually, first we're replacing this with we're replacing the sigma with sigma 0 divided by pressure. And again, this is another thing where the pressure is there. So in an undefined pressure. So yeah, so we're going to insert a derivative. So P0 minus PL divided by L equals the derivative negative dP dz. And that's because a derivative is the final value minus the initial value over the final position minus the initial position. And that's usually over like an instantaneous, like a very small interval. But if it's linear, the interval doesn't need to be very small. So because the pressure has a linear relationship with the length, we could just use the n values for that derivative. But if it's like a curved function, obviously the derivative at the beginning of the curve is not going to be the same as the derivative at the end of the curve. So you're not always just going to be able to make this leap here in terms of the derivative. So yeah, it's negative because this is the initial value minus the final value, not the final value minus the initial value. So yeah, replace P0 minus PL divided by L with negative dP dz. And that's what we do. So now we separate and integrate. The dz is just going to go on the L or on the mass flow side, and the dP is going to stay on this side because there's pressures on this side. And now we're integrating with the bounds of the system. Obviously 0 to L for the length, it's pretty obvious, and PL to P0 for the pressures. Again, that's somewhat obvious. And the negative sign in front of this is because there's a negative sign here. So yeah, pretty simple integration. Yeah, I distribute the pressure here to these terms just to make it so a little simpler. So it's a little simpler. Yeah, just the integral of just one is just the variable, and the integral of p is just p squared divided by 2. So that's where that comes from. And now we're actually doing the boundaries. So just do that and you get this. And then divided by L, so you could just, well, first separate out common terms, I guess. Yeah, so that's P0 squared minus PL squared, and you get R to the 4. Oh, yeah. Okay, so yeah, you get these two terms. Yeah, you get that. And then you have P0 and PL here. So that's R cubed sigma 0. So yeah, that's just factoring stuff out, making it look nicer, I guess. So yeah, expand P0 squared minus PL squared. And again, this is kind of just like out of nowhere. Like, where does this algebra even come from? Yeah, you basically just need to like just try random stuff and until it works. Like, if you're just doing this problem for the first time and just like getting started in the subject, it's kind of hard to like know, like, okay, why am I even doing this? Like, once you start doing these problems a lot, though, you'll start to figure out just like by it's like intuition what you need to do. But yeah, so P0 squared minus PL squared um, equals this. So um, yeah, so P average is 1/2 this. So P0 squared minus PL squared equals 2P average, and that's because there's this 1/2 here. So you have to multiply it by 2 to get P0 minus PL. So yeah, so this term here equals, or sorry, this term here equals 2P average. So yeah, this equals 2P average times that. And so we're dividing 2P average, we're dividing this out of the parentheses, and that's because, why is that? Dividing and multiplying it out of the parentheses. So like you look, it's because it's in the denominator here. So I guess you just, I don't know, I guess you're just supposed to know that somehow. So yeah, divide that out of the parentheses. Let's see. So, yeah. So yeah, there's the 2P average. So yeah, it's this term that has the P average in the denominator. Yeah, that makes sense. And this term just gets eliminated. And it's, yeah, okay, that makes sense. Yeah, that makes sense. So yeah, remember that rho equals rho 0 divided by P0 times P. So P average, or rho average equals rho 0 divided by rho P, or divided by P0 times P average. And so yeah, we're just, where is P average? There's supposed to be parentheses here. Yeah, so that's, you combine this here and this here. So that's where that is coming from. So these terms combined equals rho average. So that's where that comes from. So that's why this is eliminated and this is replaced with rho average. And then we're just multiplying 8 out of the parentheses and divided by L. And that's just to match this formula here. There's the 8 in this side of the equation and not the other side of the equation. Yeah, so now we're going to divide r to the 4th out of the parentheses, and that's again just to match this equation here. Yeah, and in this final equation, there should be an r to the 4th here. I just didn't put it, like, so you're dividing out of the parentheses here, and then you have to multiply this term by r to the 4th. So there should be r to the 4th here, but I didn't write it. So yeah, that's the problem, and this is the final answer. If you have any questions about this problem, feel free to comment about that. If you have any questions about any other problems in like the first 3 chapters of each section of the book, comment and ask me to do those problems. If you have any suggestions, comment about that. Please subscribe if you are gonna watch more of the videos. And thank you. Have a nice day.